The topic of this video is identifying the turning points and end behavior of a polynomial function. Let's look at a problem. For f of x equals negative 7x squared times the binomial x squared minus 7, find, part C, determine the degree and maximum number of turning points. Part D, determine the end behavior. All right, well, we've learned that there are two ways to determine the degree, and there are two ways to determine the end behavior. So in this video, we're going to take a different approach. We're going to use the distributive property. We're going to rewrite our function as negative 7x squared times x squared is negative 7x to the fourth. Then, negative times negative is positive. 7x squared times 7 is 49x squared. We've now converted our function from factored form into standard form. It turns out finding the degree and the end behavior is very easy once your function is in standard form. Let's go ahead and do both of those things now. Okay, the degree of a polynomial written in standard form is the largest exponent of x needed to write that polynomial, which in this case is 4. So the degree is 4. To determine the maximum number of turning points, we'll use the math elevator. The degree is 4, so we'll put the d car on the 4th floor. We'll remember d over t, which means that the t car can be in any of these positions here, but the maximum number of turning points would be on the 3rd floor, so the maximum number of turning points is 3. Part D, determine the end behavior. Well, the end behavior for a polynomial in standard form is its first term, the leading term. So we write y equals negative 7x to the fourth. As a reminder, end behavior is telling us what the graph looks like very far from 0. So if I were to draw the curve y equals negative 7x to the fourth and look at it very far from 0, and if I were to draw the function f of x equals negative 7x squared times the binomial x squared minus 7 and look at it very far from 0, the two functions would be nearly identical. End behavior is a good way of telling us what our function looks like very far from 0. All right, that completes this problem.